the feasible region, and feasible solutions. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lesson, we practiced the essential skill of taking a complex, real-world scenario and translating it into a mathematical model. We learned how to define an objective function, which represents our main goal, and how to establish a set of linear constraints to represent our limitations. However, there is a crucial distinction we need to make moving forward. Up until now, you might have been thinking in terms of exact equations, but these constraints are actually inequalities. This is a very important point because an inequality doesn't just represent a single, thin line on a graph. Instead, it represents an entire region or area on the coordinate plane. So, in this subsection, our focus will shift from just writing equations to visualizing them. We are going to learn how to graph these inequalities to identify the specific area where all our constraints overlap, the area where a valid solution is actually possible. By the end of this lesson, you'll be able to look at a graph and pinpoint exactly where your optimal solution lies. 1. The feasible region. Think about when we graph a linear inequality. Something like a x plus by is less than or equal to. See, this doesn't just give us a thin line. It actually represents what we call a half-plane. This means everything on one side of the line, a x plus by equals c, is included. Now, in a real linear programming problem, or LPP, we aren't just dealing with one single inequality. We usually have a whole set of these constraints working at the same time. This brings us to our formal definition. The feasible region is the common region, the intersection, where all of these given constraints are satisfied simultaneously. It is the sweet spot where every single rule we've laid out is obeyed. So how do we actually find this region on a graph? I want you to follow these 4 steps. First, graph the boundary lines to do an equation. For example, if you have a less than or equal to sign, just treat it as an equals sign so you can plot the line on your Cartesian plane. Second, determine the half-plane. Once your line is drawn, you need to figure out which side of that line to shade. A very reliable trick is to pick a test point, like the origin, 0, 0. If plugging 0, 0 into your inequality makes the statement true, then you shade the side of the line that contains the origin. Third, apply non-negative constraints. In the real world, we are usually measuring things like time, money, or materials, which can't be negative. Therefore, we almost always have constraints where x is greater than or equal to 0, and y is greater than or equal to 0. This is a huge help because it tells us that our feasible region must be located within the first quadrant of our graph. Finally, find the intersection. After you have shaded the regions for all your individual constraints, look for the area where all those shaded parts overlap. That specific overlapping area is your feasible region. Now that we understand that our mathematical models are made up of inequalities rather than just single lines, let's dive into our first major concept, the feasible region. Once we have identified this region, we can move on to our next topic, distinguishing between the points that live inside this region and those that fall outside of it. 2. Feasible and infeasible solutions. Now that we have learned how to identify the overlapping area known as the feasible region in the previous slide, we can move on to a very important distinction. Once you have identified that specific region on your graph, you can categorize any point, let's call it x, y, anywhere on the coordinate plane as either a feasible solution or an infeasible solution. Let's break this down into 2 clear categories. First, we have the feasible solution. A point, x, y, is considered a feasible solution if it satisfies every single constraint of the problem. If you are looking at your graph, you can identify these visually. Any point that lies inside the shaded feasible region, or even any point sitting exactly on its boundary lines, is a feasible solution. Essentially, if the point passes the test for every single inequality provided in your linear programming problem, it belongs in this category. On the other hand, we have the infeasible solution. An infeasible solution is any point, x, y, that violates at least one of your constraints. Visually, these are the points that lie outside the shaded feasible region. It is important to remember that there is no such thing as a partially feasible point. Even if a point satisfies 3 out of 4 constraints, if it fails that fourth one, it is strictly considered an infeasible solution. In the next slide, we will see how we use these feasible solutions to find the one specific point that is actually the best one, which we call the optimal solution. 3. The optimal solution. Now that we have identified the feasible region and understand how to distinguish between feasible and infeasible points, we arrive at the ultimate goal of linear programming. You see, once we have shaded that overlapping area we discussed in the previous slide, we realize that there isn't just one single point inside it. In fact, there are infinitely many feasible solutions within that region. However, in the real world, we aren't just looking for any valid option. We are looking for the best one. This brings us to the definition of the optimal solution. An optimal solution is a specific feasible solution that provides either the maximum or the minimum value of our objective function, which we represent as z. To make this more concrete, let's look at 2 common scenarios. First, if our objective is to maximize profit, perhaps for a business like the bakery we will look at in the next slide. The optimal solution is the specific point within our feasible region that results in the highest possible value for z. On the other hand, if our goal is to minimize cost, such as reducing production expenses, then the optimal solution is the point in the feasible region that gives us the lowest possible value for z. So, while the feasible region gives us all our possible choices, the optimal solution identifies our best choice. Real-world example, the bakery scenario. Now that we have understood the theoretical definitions of feasible and infeasible solutions, let's put everything into practice with a real-world scenario. Imagine a baker who produces 2 different items: cakes, which we will represent with the variable x, and cookies, which we will represent with the variable y. The baker's production is limited by 2 main resources: the amount of flour available and the total oven time. Let's look at our specific constraints. First, the flour constraint is 2x plus y is less than or equal to 10. Second, the hungry oven time constraint is x plus 2y is less than or equal to 8. And, as we discussed in the previous slides, we must include our non-negativity constraints, meaning x is greater than or equal to 0 and y is greater to or equal to 0. To solve this, we will perform a step-by-step analysis. In step 1, our goal is to identify the feasible region. To do this, the baker first graphs the boundary line for the flour constraint by treating the inequality as an equation, 2x plus y equals 10, and then shades the side of the line that includes the origin. Next, we graph the boundary line for oven time, which is x plus 2y equals 8, and again, shade the side towards the origin. Because of our non-negativity constraints, we only care about the area in the first quadrant. The area where all these shaded regions overlap, which forms a polygon, is our feasible region. In step 2, let's practice testing for feasibility, just like we defined in the previous slide. Let's take the point 2, 2. If we plug this into our flour constraint, 2 times 2 plus 2 gives us 6, which is indeed less than or equal to 10. If we check the oven constraint, 2 plus 2 times 2 gives us 6, which is also less than or equal to 8. Since this point satisfies every single constraint, we call the point 2, 2 a feasible solution. Now let's look at a point that fails. Consider the point 6, 1. When we check the flour constraint, 2 times 6 plus 1 equals 13, which is not less than or equal to 10. Because this point violates even just one of our constraints, we must classify the point 6, 1 as an infeasible solution. Finally, in step 3, we move toward finding the optimal solution. Suppose the baker's profit function is defined as z equals 50x plus 20y to find the best possible outcome. The baker doesn't need to check every point in the region. Instead, they simply evaluate this profit function at the corner points of our shaded polygon. The specific corner point that results in the highest value for z will be our optimal solution. In the next slide, I will highlight some common pitfalls to watch out for when performing these calculations yourself. Common mistakes to avoid. First, let's talk about ignoring non-negative constraints. It is very easy to get caught up in graphing the main lines and completely forget to apply the constraints where x is greater than or equal to 0 and y is greater than or equal to 0. If you forget this, your shaded region might bleed into the second, third, or fourth quadrants. But remember, in the real-world scenarios we've discussed, like our baker example, you can't produce a negative number of cakes or cookies. Always keep your region restricted to the first quadrant. Second, watch out for boundary confusion. I often see students hesitate when deciding if a point sitting exactly on a line is part of the solution. Here is the rule to remember. If your inequality uses less than or equal to or greater than or equal to, then that boundary line is officially part of your feasible region. The edge is included. Finally, do not fall into the trap of assuming that any point in the first quadrant is automatically feasible. Just because x and y are both positive doesn't mean the point satisfies your constraints. As we saw in our bakery example, a point like 6, 1 might be in the first quadrant, but it still violates our flower constraint. A point is only feasible if it satisfies every single inequality in your model simultaneously. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. I've seen many students lose marks on exams not because they don't understand the logic, but because of these 3 specific mistakes. Keep these 3 points in mind, and you'll be well on your way to mastering linear programming. Let's move on to our final summary slide to recap everything we've learned today. Key takeaways. All right, we have reached the end of our lesson. To wrap everything up, let's take a final look at this summary table. This is a great tool to keep in your notes for quick revision. First, let's review the feasible region. As we discussed when we were graphing those inequalities, the feasible region is simply the set of all points that satisfy every single constraint we've been given. Visually, if you are looking at your graph, it is that specific overlapping shaded area where all your constraints meet. Next, we have the feasible solution. While the region is the entire area, a feasible solution is just one specific point, or coordinate, that satisfies all the constraints. If you pick a point that lies anywhere inside that shaded area, or even right on the boundary lines, it is a feasible solution. On the other hand, we have the infeasible solution. As we saw in our bakery example with the point 6, 1, an infeasible solution is any point that violates even just one of our constraints. Visually, you will find these points located outside the shaded region. Finally, let's look at the optimal solution. This is the most important point in linear programming. The optimal solution is the specific feasible point that maximizes or minimizes our objective function, which we called z as we learned. While there are many points in the region, the optimal solution is usually found at one of the corner points or vertices of the feasible region. I hope this summary helps clarify the relationship between these 4 key terms. If you can master these distinctions, you'll have a very strong foundation in linear programming.